Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. This is the penultimate lecture of this course, and in today's lecture we will discuss about the basics of functionally graded composite materials or FGMs. In the last lecture we learned about the basics of wood, which we learned is a very important naturally available structural material, and we learned that wood possesses very attractive and important properties, which is very important for cellular materials, like it has a very large amount of pore. Also wood possesses a strong anisotropy, whereby we learned that the properties along the cell orientation direction, that means along the trunk direction, are much higher and the transverse properties are much poorer. At the same time, we also learned that wood possesses structural gradation, that means the structure of the wood actually varies along different length scales to actually provide different levels of support against the applied load. We also learned about the different classifications and structures of wood, and we also learned about the factors that affect the strength and stiffness of wood. Hereby we learned about the moisture content and the effect of the specific gravity of the wood on the properties of wood. In today's lecture we will learn about the fundamental definition and properties of FGMs, and we will discuss about three basic properties of common FGMs such as hardness, flexural strength and tribological behavior. The main keywords of importance for this lecture are FGMs or functionally graded composite materials, the gradient structure, discretely graded materials and continuously graded materials, then hardness, flexural strength and tribological behavior. Now, this slide actually defines what is an FGM. So, as we learned at the very beginning of this lecture that the bulk materials can be classified into different groups. Among them, the most well known monolithic materials are typically metals, ceramics and polymers. At the same time, we also learned that monolithic metals, ceramics and polymers are often insufficient to actually provide sufficient properties for advanced applications, and because of that we devise composite materials where two such monolithic materials are combined in one material in different proportions to actually provide better mechanical properties or better properties which is not achievable with any of the monolithic materials. We learned that the main application of the composite materials are to provide materials which can have properties in the material property charts not achievable with any of the monolithic materials like metals, ceramics and polymers. And we also learned that typical composites are like having like typically composites can have, for example, like a particle reinforced composites have this kind of a morphology where it has particles distributed along throughout the structure, or we can also think of fiber reinforced composites like something like that, where the fibers are all along one particular direction and in a transverse plane we have kind of this kind of an distribution, right. Now, the basic feature of this conventional composite materials is that whatever distribution you have in the material, this is mostly homogeneous. That means, although the composite materials are inherently heterogeneous material, that means if you take a very small length scale, that means if you assume that this is your length scale, then you will typically see that in the very small length scale the composite material may be non-homogeneous. However, if your length scale covers the whole sample, then you will typically observe that the composites are homogeneous macroscopically. That I mean the conventional composite materials fabricated using conventional tools. However, these conventional composite materials, although they are very attractive because they provide better properties over the bulk monolithic materials like metals, ceramics and polymers, still they suffer from the limitation that we cannot have different properties along different at different spatial locations. For example, suppose we want a material which should provide us with good wear resistance at the surface and high toughness inside the core of the material. So, in such a material, as we know, to have good wear resistance, the material should have sufficiently high hardness. At the same time, we know that if the material, typically metals, have high hardness, its toughness will concomitantly be lower. That means, it is extremely difficult to design a material with these contradicting properties. So, some examples or some schematic examples are being shown over here, where actually a solution to this problem has been found out, and that is called FGMs or functionally graded composite materials. So, as you can see over here, in A, B and C in the schematic images, typical A, in image A for example, this is showing a typical particle reinforced FGM. That means, we have a composite material where actually the particle content, here the red dots are the particles typically. So, the content or the amount of the particle typically varies as we move inside the material. So, because we know typically if we reinforce a metal with a ceramic, because ceramics possess high stiffness and also high hardness. So, those regions where we have high amount of ceramic, those regions will have a higher hardness, whereas those regions where we have less amount of ceramic, those regions will have lower hardness. At the same time, because metals have good toughness, those low hardness regions will typically have a high toughness value. So, typical example is being shown over here. So, here you can see this particle reinforced FGMA has been designed in such a way that the top surface has very high ceramic content. So, top surface will have a high hardness and wear resistance, and as you go towards the depth of the material along this direction, you typically have lesser amount of ceramic content, which will mean that the core or inside of the material or these regions, these will have a higher amount of toughness, and that will actually provide more damage resistance. Similar drawings or similar designs can be made using the fiber reinforced composite as is being seen in image B, and also for the interpenetrating composite, where we have the ceramic not in the form of a particle, rather it is a foam kind of structure, where actually kind of it is a reticulated ceramic structure, where the pores per inch or the amount of pores actually increases as we go from top to bottom, and again providing kind of a graded structure. That means, on one side we have a different morphology, and on the other side with distance the morphology continuously changes. So, typical practical example of such an FGM is being shown over here. So, this material was designed in our group, and as you can see, this is the 4 layered macroscopic sample. So, here again the aim was to have a very high hardness and wear resistance on the surface and good toughness and ductility inside the material. So, what we designed? We designed a 4 layered composite as is being shown over here, where the bottom layer, which is being marked by this red arrow numbered 1, this is the layer having a very high amount of silicon carbide. That means, this composite was fabricated using spark plasma sintering using powder metallurgy route, and as you can see the SEM images are being shown on the right hand side. So, you can see in the top layer, which is the layer marked with A1, we have large amount of silicon carbide particles, and the aim of this layer is to provide sufficiently high hardness and wear resistance. And as we go deeper inside the material from layers 1 to 2 to 3 to 4, we can see that continuously the silicon carbide content is decreasing, and the layer 4, which is this region, which is below this region, you can see that this region is actually there is no SiC particles at all, and this is a pure aluminum region or pure aluminum layer, which should actually provide very good toughness to the whole component. So, this is a very typical example of a graded or FGM composite. Now, this gradation of the properties to have different properties at different length or different thickness, can also be obtained using a laminate structure. So, as you know that in a laminate structure what we can do, we can have individual lamina like a ceramic lamina or a metal and those laminates or laminas can actually be joined to each other by some roll bonding or cladding or whatever. But when we have such laminates joined to each other, then there is a very big drawback is that in such a laminate we have a very sharp interface, because this was one lamina and on the upside we have another lamina, and these laminates or these actually they have been joined together, and because at the joint then there is a sharp interface, and this sharp interface can actually act as a position of weakness, because when loaded the cracks and the lamination can easily take place along those interface regions, and that will actually make those structures inherently poor. In a gradient structure, in comparison we have no such sharp laminates or such sharp interface. So, as you can see over here as you move from your region 1 to from 1 to 2 to 3 to 4, we have a definite structural gradient, because as you can see from 1 to 4 as you are moving, there is a significant and drastic drop or change in the SiC particle content. However, there is no sharp interface and there is a continuous change in the composition. So, this is a big advantage of the FGM structure over the laminate structure, that in the FGM you do not have that strong or sharp interface which can actually give rise to delamination. Now, in terms of the gradient structure, the FGMs can have two different classifications. They can be either called discretely graded composites or they can be called continuously graded composites. In discretely graded composites, you typically have a distinct interlayer composition variation. That means, again I go back to the previous slide. So, again you can see here as you move from 1 to 2 or 2 to 3, there is a distinct change in the composition, right. That means, although there is no sharp interface, we can definitely identify there is a continuous interlayer region where the composition changes. So, these are examples of discretely graded composites. At the same time, there are also examples which I will be showing in the next lecture tomorrow, that these are called continuously graded structures, where although there is a gradation, but this gradation is continuous. There is no such distinct change as is being observed in the discretely graded composites. Now, the question is, these FGMs, they are extremely attractive materials for technical applications. Now, how to design such an FGM structure? Now, the easiest or the basic way to design such an FGM is to have a graded volume variation. That means, we have to design a composite with different volume fractions of the individual constituents along the length or thickness of the composite material. And again, as we learned, there are two different types of gradations, either discrete or continuous, and based on that different relationships have been established to actually define the gradation and also control the gradation. So, the left hand table, as you can see over here, this left hand table, these actually provide some examples to actually control the composition of the continuously graded FGMs. That means, in these cases there is not a discrete variation, it is a continuous variation of the composition, and how those compositions can be varied, these are the expressions for varying the or controlling the volume fraction. And the expression on the right hand side, this is actually the expression for the volume fraction control of graded composites with discrete gradient. Okay. And now, if we try to plot these expressions, so for a graded composite, so typically you can see for a continuously graded structure, if we have different values of the constant, in this expression, as we know, this constant, this small n is actually a material, is actually a design constant which actually controls that how the gradation will be will manifest itself. That means, this n can be controlled to give different levels of gradation, and correspondingly we can see over here, if we vary the value of n, so this z over h, so h is the overall length of the composite, and Z actually shows the varying length as we move from one surface of the composite or the FGM to another surface of the FGM. So, as we vary the Z over H and we have different values of N. So, we can see that the volume fraction of the individual phases inside the composite will typically follow these lines which is being shown over here. So, these lines actually allow us to design the FGMs with different compositions, and as we know, as we vary the compositions, the properties will also vary according to our will. Also, for discretely graded composites on the right hand side, again we have this expression over here, where small p is the individual layer number and capital N is actually the total number of layers we want to design in the FGM structure, and again small n here as your exponent. This small n actually again denotes the this controllable constant, which actually gives the degree of gradation and amount of gradation and also the volume fraction of the individual phases in individual locations of the whole FGM structure. And again, if we take different values of n like 0.1 or 1 or 2, we have different gradation structure as is being shown on the right hand side. So, this way we can see that we can easily control the gradation structure in an FGM material, and this actually allows us to vary the volume fraction of the individual phases in different regions, and by doing that we can make tailor made materials with different properties along different regions. So, some examples will now be discussed with you. So, first we see the influence of the gradation structure of the FGM structure on the hardness of the materials. So, different materials have been fabricated and hardness of the FGMs have been studied intensively, and as you can see over here. So, different examples are being shown over here. The image A typically shows a composite or an FGM material with copper as the bottom layer with typical red color appearance of copper, and the top layer has tungsten. So, tungsten, as you know, it's a very heavy material with a very high melting point, and copper, it's a very highly conducting material, and these copper tungsten materials, they have extremely good applications in the future fusion reactors. Now, it's a very big challenge to actually join the tungsten and copper together because of the very high difference in their thermophysical properties, but in this case this FGM structure was fabricated by powder metallurgy route, and as you can see, as we all know that copper is a very soft and ductile material and tungsten is a very hard material. So, as we keep on increasing the tungsten content from bottom to top, as we move from the copper rich region to the tungsten rich region, we can see that the hardness increases by almost 1 degree of order, like in the copper region around 50 Vickers hardness to in the tungsten up to more than 500 Vickers hardness. Similar hardness measurements have been carried out for many other FGM structures, like in image D, for example. Again, one composite has been fabricated with one side as molybdenum and the other side as aluminum nitride, and as we know that aluminum nitride is a ceramic material, so has a higher hardness and molybdenum has a lower hardness, and again we see that if we vary, so here actually we can see here the different values of the exponents. So, the value of the exponent p over here is equivalent to the exponent n, which we mentioned, which we introduced in the last slide. So, you can see that if we vary this value of the exponent p, we can have different degrees of gradation, and accordingly we can design an FGM structure with a very with a widely varying hardness level in different regions of the composite material. Also, in image E, for example, silicon carbide particle reinforced metal matrix composite was fabricated, and again we can see there are different regions are there depending upon the fabrication process, which we will see in the next lecture, and we have regions like chill zone, outer zone, transition and the inner zone, and the outer zone actually the outermost portion, it is rich in silicon carbide, and correspondingly this region has a very high hardness, and as we move inside the material to the inner surface, which is actually devoid of any ceramic reinforcement, in that region we have a very low hardness, because the typical metals like aluminum or magnesium, they possess a low hardness value. Another example was actually of such FGM was actually made in our research group. So, here actually we fabricated one composite material on FGM composite with ZRB2 and B4C. That means, as you know, The ZrB2 is a very high temperature composite, high temperature ceramic, because it is a very high melting point, and B4C is a very attractive material, because B4C has very high hardness. It is the third hardest material after diamond and boron nitride. At the same time, B4C possesses very low density. So, these kind of composites, like these composites can be actually very attractive for high temperature aerospace applications. And now we actually made one composite material or on FGM material with high ZrB2 content on the top surface and high B4C content at the bottom surface. And what we actually observe here is that as we move from the top layer on the right hand side, we can see, because ZrB2 has a lower hardness than B4C. So, as we are moving from the top layer to the bottom layer, our hardness actually continuously decreasing. At the same time, we can say that there is no visible defect at the interlayer region. So, you can see these blue indentations have been made at those regions where we have a transition from the layer 1 to layer 2 to layer 3, but we can see that all those individual interlayer regions are fully defect free, and because of that we do not have any hardness drop at the interlayer regions. So, again significant studies have been carried out on hardness, and this slide typically shows that how the hardness of the FGMs vary depending upon the constituent and also the number of layers inside the materials. Apart from hardness, the flexural strength, which is nothing but the strength under bending, either 3-point bending or 4-point bending, it has also been measured, and the flexural strength of FGMs also show a large scatter. That means, here again these individual the vertical distance of the individual bubbles, they actually show the difference in property in one particular graded structure as we move from one side to the other side. So, again typical example of the flexural test on such graded structures have been shown are being shown over here. The left hand side, you can see over here, again it is a graded structure where the blue portion of the blue layer is basically the metallic layer, and the black and the gray layers, so actually basically shows that as we increase the amount of boron carbide composite in the layers, it is being shown by more darker texture. That means, as you can see, the blue layer is the pure metallic layer, the dark gray layer, that means the other extreme layer is actually the B4C rich layer. Now, as we know, if we perform a bending test, as is being shown on the right hand side over here, we have in such a bending test, we have in a 3-point bend test, the point at which the upper platen or the upper punch is in contact. So, this surface will be, because in the bending the sample will be like this. So, the top surface will be under compression, so negative stress, and the bottom surface will be under tension. So, if we load it like this, so there will be tensile strain at the bottom surface and compressive strain at the top surface, and there will be one portion which is called the neutral axis. That means, you have something like this, at the middle there is a neutral axis, and then there will be the stresses will be like this. So, this is the positive side and this is the negative side, right. And as we know that when we load any ceramic rich material or ceramic material under tension, then ceramics are extremely poor. I mean, because ceramics, they cannot sustain tensile loading, and as we put the ceramics under tension, they will break easily. And as a result, you can see over here that when we put the on the left hand side, when we put the metallic phase or the metallic layer under tension, as in image A, we can see we have a flexural strength of almost 1300 MPa, whereas if we are now putting the metallic layer under tension under compression and the ceramic layer under tension in the image B, that means the same sample we simply rotate the sample and put again under compression under bending, then we have a much lower bending strength. So, again we can see that the FGMs actually provide a very good opportunity actually for the same composition. Just by changing the orientation, we can have vastly different properties in the material. The same example or similar example is also being shown in one of our work that I discussed earlier. Again the same aluminum SiC composite is being shown over here, and again you can see the loading condition 1, that means in the table is being shown over here. The loading condition 1 corresponds to the situation where actually the metallic region or the aluminum rich region is at the bottom, that means under tension, and the ceramic rich region, as you can see, which is at the top, that means under compression. And the orientation 2, I mean the orientation B, that means 1A means the metallic region is at the tension and ceramic is in the under compression, and 1B means the ceramic is in the tension and metallic layers are under compression. And this way we have 4 different compositions, and we can see the failure stress actually depends strongly on the type of orientation we have. When the metallic layer is again under tension, we have larger flexural strength than when the ceramic layer is under tension, because again as we discussed earlier, the ceramics they cannot survive under tensile loading. That means when the ceramics, when the crack initiates at them, then it can propagate very easily, and that will actually lower the strength of such FGMs significantly. Again the typical fracture morphology of the FGMs are being shown over here, and as you can see that in image A, this is the aluminum layer, and as we move from the aluminum layer to the more ceramic rich layer, again image B shows the interlayer region, but again you can see that there is a very good interlayer region. This typically this region over here where the fracture mode changes, but again there is no delamination over there, and also there is again some kind of a interlayer region over here, but again at the interlayer region there is no such change in the damage mode, and the damage mode, I mean, but the different regions of the FGM are shown, whereas that one region is like no ceramic is there and it undergoes ductile failure, whereas the other regions with more ceramic region is kind of more cleavage failure. Also the FGMs are very attractive, as I already mentioned, for tribological applications, because they actually provide the ability to actually have more wear resistance on the surface and higher toughness at the core. And similar examples are being shown over here in image A. For example, A, B and C is the same sample, but wear testing has been carried out at 3 different regions. So in the outer region, as you can see, we have very tiny groups, because this region again possesses the higher hardness, that means the wear rate is much smaller over here, whereas in image C, which is a much softer area of the whole composite, we can see that because of the much softer area and much lower hardness, we have significant delamination and large groove and debris formation over there. So again the graded structure actually allows to control the wear behavior from outside to inside. Again we can see the image D, the amount of weight loss because of wear, and again we can see that depending upon the area of the sample, the higher hardness regions will provide lower wear and vice versa. Also it is also possible to actually typically add such materials as graphene or graphite as self lubricating elements. These elements typically have a very low hardness and mechanical properties. So if we add those materials kind of uniformly in a sample, then the sample hardness and mechanical properties will be inferior. But if we, because only the top surface is undergoing the wear behavior, if those self lubricating elements are preferentially added only on the top surface, then they will provide good wear resistance at the surface. At the same time, the whole mechanical properties will not be sacrificed. So we can see that FGMs actually provide a very attractive route to design materials with different properties and microstructure in different directions and different locations, and that will actually provide very good applications for many challenging applications. So to conclude, in this lecture we learnt about the basics properties of the FGMs and their structures. We learnt that the FGMs can actually be designed depending upon the amount of volume fraction of the phases we require in individual locations, and they have a big advantage over the laminar composites because they do not have the sharp interface, which is a big drawback for the laminates, because these sharp interfaces can actually provide regions of delamination. At the same time, we learned that it is possible to design materials in FGMs with mutually conflicting properties like high hardness on the surface and good toughness inside the at the core of the material. So, the main references for this lecture are being shown over here, and in the next lecture, which will be the last lecture of this course, we will discuss about the various processing techniques for the FGM materials, both metal ceramic, metal and also ceramic composites. Thank you very much.